Hey everyone, how are we doing? It is office hours on the Tuesday. Is everyone having a good morning right here? We'll see who's all in the chat. Mubot is here. If you're in the chat, feel free to say hi. Just message out on the Discord. See if some people join in. There we go. Quiet day on the Discord. Got some DMs. Check them out a little bit later. Hey, what's up, Fred? Good to see you here. Hey, Kyle, what's up? Drop some questions if you got them. We can start working on some questions. Let's throw out 1,000 Mubot points. What questions do you have right now? Drop those questions in the chat. Awesome. Good to see you here. If you got questions, let us know. I'm going to catch some Pokemon Day. BS 340? 340 or 320? 340 or 320? I don't know. I know 340 a little bit. Haven't done 340 in a little while. I think some 320, right? Some 320? Is that the plan? I don't usually teach 340. So, good morning, Meath. Good to see you here. I need to put up a weekly coding for this week. Weekly coding. Thank you to everybody. We got a lot of people. We got the hiccups. 320. We got a lot of people working really hard on their weekly coding. Submit 50 lines. 50 lines. Okay. Make sure in your weekly coding, I can't even speak, to turn in, put it here back to Thursday. Save and publish. I just came by for, 340 stuck in your head. I'm starting 474. Can't get the first U to load item frequency function. A rules. So Kyle, make sure you have A rules going here. We'll take a look at that really quick. Then we're gonna do 320 next. Let me save that graphic I was working on, some graphics in the term. So Kyle, here, let's do that. Starting, and then we're gonna do 320 next. So this is 433 BS 474, starting the assignment. Okay, here we go. Let's check it out. So item frequency is located where? So Kyle, you might have to message me because a few people have had problems installing things. You need to make sure you have library A rules going. Does this work right here, Kyle? When you do this, does that run? Like, does this populate? Always don't let autocomplete do its thing, because if autocomplete's not doing its thing, then it's not there. And if this doesn't work, we might need to meet, and I might need to help you out with getting it. It might not be installed. So that might be the issue. And you might have a problem. A few people have had issues with their install. That works. So now when you run that, you should have item frequency, and there you go. So it autofills. Nice job right there. Matt's got some while loop stuff. And I think a few more people are still taking it, Matt. So we might have to wait till tomorrow, because we have a few people like finishing up. Some people had some flights and stuff that precluded them from taking it during the given time. So Matt, or message me on Discord, because we don't want to, like, you can't send anyone your work and stuff like that. So I could probably send you the answers on, or like how to do it on Discord. I've already talked to a few people, because you don't want to like say to anybody like how to do anything after coding night too much. So Matt, let me know. Good questions there, Matt. And Kyle, when you run this, does this fix it up? I want to get Kyle here started on the assignment. Then we're going to talk 320 next. So 320, hang out. We're going to be talking some questions right here. How does that work right there, Kyle? Is it now giving you item frequency? Gives me your error in evaluation argument X in selecting a method for item frequency, the cure not found. So when you have your item frequency right here, do you have your transaction data stored into something like music? Now that's not going to work because music. Does this work right here just by itself? Does that? Oh, I think what you have is you might have something like the cure like this. Do you have the cure like this right there? So always try the code by itself to start. Like this should run. If you have it stored into music, that should run. So does that run right there? Now there's a problem. Music by itself works. Good stuff. Is this what you have right here? Yes or no? Like, do you have it written like this? Do you have it written like this right here? Because I think you might, by the way the arrow looks. Gosh, I've been doing this for a while. I'm like, the arrow looks like it's written like this. Because, oh, you're using a $sign? So we won't put a $sign on it. This right here should be in quotes. Oh, so you're doing like, you were doing $, the cure right here. But I don't have music right now. You don't want a $sign because that's like within a data frame. You want to go here and put like Ben Folds or something like that, and that'll look for the position in the vector. So item frequency returns a vector, and then when you put the square brackets and the quote for the item, you're finding, no worries, Kyle. That's what we're here to do. Kyle, 1,000 points. This is now that you see, it's like, oh, that's how you do it right there. So Kyle, thank you for asking. That's why I did this one first, because I figured that'd be a quicker question. I wanted to get the ball rolling on you doing the assignment. So thank you for starting early, Kyle. Once you see it, you're like, oh, that's how you do it. Oh, come on. But no, that's what we're here to do. We're here to solve those problems, and good work right there. That's how you use the item frequency right there to find it. Good stuff. Now let's go over and talk about some 320. 320. Okay, 320. Olivia and Meath right here. Drop those questions in the chat because we're about to do some 320, and let's take a look at your assignment. Are you ready for some football? Yay, 320. So the whole point, let's drop this in right here. Got some Peyton Manning in the chat. One of these days, my goal is to get Peyton to come to our class. He's always welcome. So this is assignment 6. He's always welcome. He's a busy man, though. He's a busy man, so no pressure, Peyton. Okay, cool. Helping my wife create some images. Error in eval, parse text. You getting that error? Do you have the data loaded up? Let's talk about starting right here, because we're going to analyze data right here. The data you're analyzing is the EX3 NFL data. So I'm going to pull up your data here for a second. So now that we have this, you need to go to library, reg class. Then you need to do data, EX3 NFL, and the data's loaded up. Oh, and then those on separate lines right there? It's 2 lines. Good. And then when you look over here in the global environment, do you see that right there? Does that work right there? How is that looking? Then you're good. Then you got the data loaded up. Now, what you also want to do is you probably want to start an RMD file, an R Markdown file. So when you start the R Markdown file here, I think it says here. We're good on that. Start an R Markdown file to create your own kind of work right here. Did that too? Nice work. And what I do want to say also is when you create this, I'm going to make a Word document. Okay, good. When you create this right here, you can actually see how it's going to look when you knit it by going to Visual. And you can actually edit this visually over here with the Visual Editor. So you can make things bold. You can delete things out. Do not delete any of this starter stuff. This is like necessary stuff. If you have problems knitting, please tell me immediately. Try knitting your assignment often. You probably just want to delete out this stuff right here. Yeah, I know, right? It's little helper things because now you can go in here and we'll just go down to here and we'll just be like start of document or something like that. Start of document. And then you could insert a coding chunk right here to start writing some code right here. And you could be like library reg class, run it right there, and data equals EX3 NFL. And now you have right here. I mean, I think this is all kind of neat. And then you go down here and you could be like, you know, I will cover whatever. You can put lists. You can do all these different things. So, you know, think about how you can make this look nice. And then if you don't like the way it looks after you knit, here, watch this. We're going to right here. We're going to knit the file. I'll show you how to do that. We're going to go knit. Going to go knit to Word. So knit to Word. It's going to save to my computer. Knitted document 2. Okay, so here we go. It's knitting the document. It's going to do it eventually. Is it not? There it goes. It's doing it. It's opening the document. So you want to try this immediately. Now, here's the thing. What do you immediately notice right here? What do you immediately notice? Like, this is what you might be turning in. What do you immediately notice? If you're turning this into your boss, what do you immediately notice? What do you immediately notice? I need to tell, why can I not think? Cecil. You don't need all this stuff. So what can you do? You go right here and you delete. Now you have to save it. It wants me to do file save as again because it's in like a read-only format. So I'm saving the file again, even though it seems redundant. I'm just going to rename it, and now it's saved. So I renamed it, saved it, and deleted. Unnecessary. Don't put that stuff in here. So now we just got this. We deleted out all that stuff. Just save it again, delete stuff out, make it look nice and pretty right here. You can retitle this right here. You can move that stuff if you want. You could say football analytics for such. You can include logos. You can do whatever you want. But the point of this is to make these look professional. I don't want people thinking we're doing a bunch of like mathy, codey stuff. We want to make it look professional. You can include a little bit of code if you want, but don't show things that just look all crazy like. Does that make sense on starting this? Olivia and Meath, how are you doing on just getting this started? You should have a RMD file created. You should have the data loaded. We should have that it knits. So we should have a start to this. How's that? Boom. Started. Awesome. Now that we have this started, starting assignment 6, let's put a new section in here called Analyzing Regression. So the whole point of this assignment right here is to do some analysis of regression. So I'm going to go back over here to my .r file, and I hope by now people understand the difference between an RMD and an R file. An R file is just a script. We can't knit this. But both regression analytics should be practically, I think the one's not statistically, right, Meath? So the one that is not statistically significant can't be practically. The first, haha. Copy paste. The second. The second one comes back as not statistically significant. So if it's not statistically significant, it can't be practically significant. Does that make sense right there? So this, yeah, the second, since it's not statistically significant, it can't be practically. I know, right? Whoops. I got this out, I think, Friday morning, and so messed up that right there. It should have said second, but we fixed that. So basically, think of this as a step-by-step thing. Like, you have to do, like, interpret the intercept, interpret the slope. So slope, intercept, you want to visualize it, you want to write the regression equation, you want to make a prediction using the regression model, create and interpret confidence intervals for the slope and the intercept, finally interpret the value of r squared and the RMSE. So we have all those tasks. So which one of those should we do right now? Which one of those should we learn how to do in practice? So this is just, you just need to know what these values are, how to find them, what they mean. What should we do first? You got to know how to make regressions. So what should we do? What should we do? Pick anything, like make the regression, visualize the regression, RMSE, R squared. What should we do? What should we learn how to interpret and write? The RMSE? Yeah, that's the root mean squared error. Can we go over the code which we're running? Yeah, and we'll do the code here in a second too. So this, we have to do the code to get to that. Good questions right there. So I want you to think about what RMSE stands for. RMSE stands for root mean squared error. So if this is root and mean and squared error, what cancels? What cancels on root mean squared error? 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 But think about the words themselves. Like, does mean cancel with something like mathematically? Root and square, Nilla, great job right there, 1,000 points. Root and square cancel. So if root and square cancel, what does RMSE really tell us? What does the RMSE really tell us? Like, if those words cancel, root and square cancel mathematically, what is RMSE really finding for us? What is it finding for us? Like, this is why it's good to understand these things conceptually and to be like, well, the RMSE is the root mean squared error. So it's actually just finding for us the what? What is it finding for us? Well, think about what we're left with. The RMSE finds the mean error, which is the typical miss the model makes. That's another way to say it. The typical miss, like how far is it typically off? Not everything will miss by this, but like the typical miss. So when you have a model here visually, a model is going to look like this right here, and then the points are going to be around the model. Does that make sense? We call a miss a what? What is an error known as? An error is known as a what for this model. An error is known as the what for a model. Like another term for error for a model is what? Another term for error is known as what? Another term for error is known as the what? It's residuals. Great job, Olivia, right there. We're throwing some crazy points. Yes, it's residuals. So why don't we just, so let's just skip this whole root mean squared error thing and just find mean error. Why don't we just find the mean error? Like, what would be the mean error of this model if we just average the residuals? Why don't we just do that instead of doing root mean squared error? Let's just find the mean error of the model and just say the average miss the model makes is this if we average all the residuals together. Well, think what the residuals do. So if you were to find mean error, it would be 0, exactly, because that's what residuals do, is some are positive, some are negative. So by squaring the residuals, all residuals become what? By squaring the residuals, all residuals become what? If we square the residuals, which is how much the model misses by squaring the residuals, they all will now become what? I'm finding a residual and squaring it. Like I'm going to how far the point is away, and then I'm just making a square around it. They all become positive. So we would find the root mean squared error, so the mean of the squared error, but then we root it to bring it back to the original units of the problem. So squaring it makes them all positive. We then find the mean of the squared units, and then we square root it to find the units of the problem, because we don't want to talk in squared units. There's an alternative to this, which I'm not a big fan of, mean absolute error. So that is the average absolute error, because it makes them all positive. Just another alternative, the MAE is the mean absolute error. There's also MAPE, mean absolute percent error, MAASE, mean absolute scaled error. There's a lot of ways to do this, but all of these are just trying to figure out how far away is the typical miss of the model, and different ways of doing it, because we can't just average them together. We have to either like square them or absolute value them or scale them, percent them, different ways of doing it. So with this is known as the typical miss the model makes. So what do you want your RMSE to be? You want it to be very what? You want the typical miss your model makes to be very what? You want the typical miss your model makes to be very what? And the typical miss would look something like this. It would be in here. Like we typically miss by about plus or minus this. It's like about on average we miss by about this much. That's about how much we miss by. Like if I predict this, I'm usually off by about this, plus or minus this. It's not an exact. It's not saying we will be off by. I predict this, I'm usually off by about this. What do you want the RMSE to be? And then we'll look at RMSE in context and make some output with RMSE. Yeah, we want it to be as small as possible, closer to 0. Like, and then it's all context dependent. Like if we're predicting somebody's salary in millions of dollars, well, then that's a big, like 1 would be a big unit, because like we're off by like 1, we're usually off by $1 million. That's a big unit difference. But if we're predicting like height, let's do one where we predict height. So this is how to make the models right here, Olivia. Check it out. We usually store, you could call it model 1. So that's just a name I'm storing into. We call LM, and then we go height. This is not one you'll be doing, but I'm just doing it for example purposes. And survey 10, I don't have survey 10 loaded. These are not ones you'll be doing right here, but that's just a model predicting height from weight. To break down what this formula says, predict the y variable from the x variable from the data frame they're contained in. Yeah, the RMSE closer to 0, the closer the points are to the regression line, because smaller the typical miss. Like bringing the RMSE down will bring the points closer to the line. Like smaller typical miss means the points are closer in towards the line, because the typical miss is measured by how far away the points are on average away from the line. So visually speaking, as Meath is pointing out right there, that if you have a smaller typical miss, then the kind of typical distance those points are away from the line is going to be tighter. So the points are going to be closer in. It's going to help. This R squared is going to go up. The standard error, the slope is going to go down. A lot of conceptual things will get better. Like conceptually, your model is a better model if the RMSE is smaller. So, okay, and the x variables for both have to be the same, correct? No, you'll do different x's. You'll use the same y. The real whole point here is to have 2 different models. The whole point of your thing is to analyze 2 different models fully. Does that make sense? Like the whole point of this assignment is to make 2 regression models and know all the output. So that's a good question right there, Olivia. And thank you so much. Olivia, keep asking those questions. The whole point of this is to make 2 models and know every bit of the output. Like when we create the output right here, How much of this output should you know? How much of this output should you be able to understand and interpret to somebody? How much of this output? We'll probably put a screen here, and so we'll start maybe with the RMSE. How much of this should you know and interpret to someone? How much should you be able to tell someone what these values mean? What percent of this should you be able to explain? Like, if I pick a number, how many of these numbers should you know and be able to tell me what that number means conceptually? And let's put this as a note right here. 2255. Let's say explaining the LM output fully. You should know every bit of it. So what is this output and what does it mean? First off, let's do the following. Let's make a visualization of our linear model we've created. And for those watching, let's just show the code we've used to make this. If you want to replicate what I've done right here, you can run the following code. I'm going to put this up top right here. If you want to run this, you will need to have installed library reg class. So make sure you've installed that. You only need to do that one time. We're using the survey 10 data from library reg class. We've created a summary and we have visualized the model. This is all the code to create the following summary output right there. So I'm going to disappear in a moment. Let's talk over this. Can you show an example of making the graph with GGplot as well? Yeah, we can do that here in a moment. You bet, Olivia. And we'll make a really cool one after this. Let's fully interpret this, and then let's talk about how to make a really cool GGplot, like a really cool one. Okay. So this is our model. Does everyone understand? The red line right here is our line of best fit, is the line that best goes through this data. If I'm looking at this model to begin with, I might notice at the end there seems to be a problem with what? Think of your stats 1 knowledge where we say 2 quantitative variables. Now the second condition is what? I'm noticing a bit of an issue here of this model at the end of it. What issue am I noticing with all the points below the line? Because the line should go through the data. There's a problem with the what of the model, especially near the end of the model. Because I don't see any points above the line. The points should be scattered around it. There's a problem with the what with this model. Well, maybe it's a little heteroscedastic, which means change in spread. There might be that, but the points all being below the line indicates to me a problem of linearity. There are also outliers, good things. That's where I would go next. Olivia, great work right there. So looking at the visualization right here, I notice a few problems. Does that make sense how I'm noticing problems with my model? The problems with the model seem to me, one, that there's a linear problem. At the end of the model, the points are not around the line evenly. We should see even points around the line at all points. There might be a little heteroscedasticity, which means the plot is thickening or thinning in some directions. We want the plot to say about even thickness, and I don't know if I see much of it. The bigger issue looks to be some outliers, maybe down here and over here. Then there's also the line not going through the data, which is not good. That's a huge condition for linear regression. So if you have linear regression, bit of a problem. So we'll ignore the problems for a moment and look at the regression output here with the summary. Put it on the shelf and maybe find a better model later when we have more techniques like polynomial regression. So the first thing you see right here is the residuals. What does this mean? What is that telling you? What does this mean right here? What is negative 21.3927? What does that mean over here? Can you find that point over here? Negative 21.3927 means what? We have to know what that means. When we look at the output and it says there is a residual that is negative 21.3927. What does that mean? What does that value mean over there on the left? That means the lowest residual that we have is negative 21.3927, and that means is below the model. That is this points right here, distance below the model. It's negative 21.39. That is the lowest. You can't always find it, but that one's a little bit obvious. So if you were to do the unit differences right here, notice how this is right here about 21 units. So that should be it right there. That looks to be the right. Yeah, it's a little bit lower. It's somewhere around 53 or something. If you trace to where it hits, this is the y hat. and that is the value of y down there. So that's the value of y, and that's the prediction right there. And the unit difference between the two is negative 21.39. So so that one, does that make sense, Meath, right there? And then you notice the 13. Can you find where the 13 is at? I think we have that one. That is correct. Do you know where the 13 is at? The value that says 13.1583 is the highest possible residual. Do you see that one there? The value that says 13.581583. Where is that one? Where is this one right here? That one is the one over here that is that many units above the model right there. So that is 13, a little more than 13 units above the model. If you do the math, maybe this is 62, and that is its y hat, which is its predicted value, and then its y value is close to 75. So that is someone who was 75 inches tall. They are 75 inches tall, but they're predicted to be 62. So they are 13 above their prediction. Does that make sense to say their residual is 13? That's the furthest above the line. Now, you want the median, the 50th percentile of residuals, to be around 0. So there's a lot of residuals to be right around here. That's what the median represents. I'm having trouble. Yeah, Kyle, we can do that here next. We're going to interpret this output fully. And this interprets a lot of what you're doing on your assignment. So this just tells you the quantiles of the residuals, telling you what is the highest residual, what is the lowest residual, and then you do want the median residual to be at about 0. And then also you want to see some symmetry in the residuals. Does that make sense? So if the Q1, the 25th percentile, and the 75th percentile are kind of close, that's better. And this is more for outliers over here. So the median residual should be close to 0. That means the linear model is doing well. If the center of the residuals is close to the line, right around the line, and then also the 25th and the 75th should show some sort of symmetry, because we want to see that we have about the same range that the residuals go out on the low and the high side. And last but not least, the min and the max can generally be looked at for outliers for residuals, which would show you the most extreme points being the one down here, which is the most below the model, and the one up here, which is the most above the model. So now that we know what this output means, we have our what's for the model. The next thing to know is our model has two things in it. A regression model for a line will have a what and a what. A regression model will have a what and a what. What two things does every regression model have in it? All regression models have a slope and an intercept. Slope and intercept right there. So the intercept is known as B0. Good way to remember that is when x is equal to 0. And the slope would be for each 1 unit increase. Well, but we go a little more in depth because we don't want to make it sound like cause and effect. We're going to talk about two people who differ by their weight in 1 pound are expected to differ in their height by so many units. So when you think about this right here, to write your regression model, and let's take a look. To write your regression model, you need to know the y variable is height. So we'd have here predicted height, which is going to have a hat on it because actual height would just be height, is equal to the slope, which is 56.34. And then we'd go plus, because it's positive, 0.07, and I'm going to round it to 3, times weight. So could you predict your height right here? If Brian weighs 200 pounds, predict Brian's height. Just try that right now using this model. If Brian weighs 200 pounds, so for RMSE, would you use rigid value? You'd use the residual standard error. Good questions, Olivia, right there. We're going to do all this output right here. We're going to interpret every bit, which answers a lot of the questions. Predict Brian's height. If Brian weighs 200 pounds, predict Brian's height. Brian has a weight equal to 200. So I've just written the regression equation. My weight is 200. That's my actual value of x. So that is value of x right here. My weight is 200. Predict my height. So I'm trying to think through 14.6. Okay, I've got the answer in my head. So what is it? Should be very close to this. Should be close to... I want to see what people get. Close. I think some decimals. Meet that's very close. Carry a few more decimals. I'm getting about 70.94 is what I'm getting in my head. So let me see here. I get 70.94. I usually do it over here so we can watch it. But we plug in, or we can just write it right here. Let's take the equation and then grab this plus times 200. Oops, attempt to apply. I forgot the times. I always forget that. 70.99. There we go. And when I rounded it, 70.94. So with the rounding, so basically you would say to someone, I predict Brian is 5'11". Does that make sense? So since you predict Brian is 5'11", and Brian is actually, so that would be predicted height for Brian from the model is 5'11". Brian's actual height, which is just my Y value, is 6'3". What could you find right here pretty quickly? Like, now that you know Brian's predicted height is 71 inches tall and his actual height is 75 inches tall, you could think what? And think of where I am visually speaking. Visually speaking, I'm over here. You can see how this traces over to about 71, and I am up here. So what can you find from this pretty quickly? What would you think of right here? Oh, then Brian's this is this. So what could we find out very quickly using this? And then what is my positive residual? And then what does that mean? I'm above the line. So then Brian's residual is what? And then what does the residual mean? Residual of 4. So what does that mean? Brian is 4 inches taller than the model predicted him to be. So by finding Brian's residual using the estimates, we have Brian is located over here. And so Brian is right here. And there's Brian's prediction. And so Brian's residual is positive 4. Does that make sense what a residual is? Brian is 4 inches taller than the model predicted him to be. So Brian is 4 inches taller than the model predicted him to be. And that's what the residual means. It's how much the model missed me by. So that is the output there. Let's go back to the summary and talk over a few more things. So in the summary of a few more things to talk about, we have here the standard error. Standard error is just another word for uncertainty. It's not literally another word, but I like to call it uncertainty. So this is, think about this. I think the slope's about 56.34 because that's my what in the slope. Like the slope. This is my what of the slope. So use the terms right here, or intercept. I'm on intercept right now. This is my what of the intercept. Like if you trace in, that's my what of the intercept. This value right here is my what of the intercept, my estimate. Slope's probably, I mean, that's the intercept. I keep saying slope. The intercept is probably about this, but I could be off by about this amount. Do you ever have a friend who says, I'll show up to your house at 3 p.m., but I could be off by plus or minus 30 minutes? That is the uncertainty. The first value right here is them saying, I'll show up at 3 p.m. That is your estimate. Residuals are how much we miss by. So residuals wouldn't be standard deviations. They're just how much we miss by. So the 3 p.m. right there, when your friend says, I'll show up at 3 p.m., that's their estimate. The standard error is, well, I could be off by about this amount. Now, it's not saying you will be. You ever have a friend who says they'll show up at 3 p.m. plus or minus 30 minutes, and then they show up at like 3:35? It's about that amount. Does that make sense what the standard error is? The standard error is, well, I think the intercept is this, but I don't know. I could be off by about this amount. It's how much you're uncertain of your estimate by. How are people doing on the concept of what a standard error is? The standard error is your uncertainty in your estimate. It's saying, I don't know. So what do you want your standard errors to be? Think conceptually. You want your standard errors to be what? You want your standard errors to be what? You'd like your standard errors to be what? Small. Great job, Amanda, right there, jumping in. You want them to be small. You don't want uncertainty in your estimates. Does that make sense? Like, this is your friend says, I'll show up at 3 p.m. plus or minus a minute. And you're like, wow, you're really certain about when you'll show up. Like, you should be here right at 3 p.m. then. So actual intercept should be, well, that's what we think the true intercept is. It's probably somewhere between that. But here's the thing, is the amount of uncertainty we have can be used to make confidence intervals. So if we were to use this right here, this value right here and times it by 2, we have the upper bound and the lower bound for a 95% confidence interval, basically. Almost verbatim. 57.17 by the rounding on the other one, and 57.52. Because now I'm going out 2 uncertainties. So the standard error right there is used when we have an estimate. Here's the estimate. And then we can go plus a certain amount of standard errors. This is 1 standard error up. This is 2 standard errors up. 3 standard errors up. -1 standard errors. -2 standard errors. -3 standard errors. So the standard error, as Meath is pointing out right there, can be used to estimate with 68% confidence. Oof, that's way too large. With 68% confidence, the true intercept at this point. I am 68% confident the true intercept is in this bounds. And generally, it works this way. It's going to be with t's, so it's close to this. With 95% confidence, I think the true intercept is in this bound. So you want your standard errors to be very what? These concepts of standard errors, you want them to be very whats. You'd like your standard errors because you're going outside your estimate. You're saying my estimate plus or minus this amount of standard errors. You want those standard errors to be very what? We don't like uncertainty. We don't like uncertainty in our estimates. So you want your standard errors to be very what? You want your standard errors to be very what? You want them to be very, very close to 0. Closer to 0, better. So when you think about this right here, it's going to find this for us. So when we run the code like confident, which is also in your assignment, you can change the level of it to 68%. And now the upper bound should be how many standard errors above. Like if I were to go right here, how many standard errors would I go above the estimate to find the upper bound of a 68% confidence interval? What's up, Alexandra? To find the upper bound of a 68% confidence interval, how many standard errors would I go up? And the visualization tells you the answer. The upper bound of a 68% confidence interval would be how many standard errors above? The upper bound of a 68% would be what? How many standard errors would I go up? And it'll do the math for us. 1. So think about this. We can find the answer to this by going to our estimate of the intercept. And on the estimate of the intercept, add to it 1 standard error. And this is an estimate of it, like it's going to do the more exact mathematics. And look at the answer right there. Is that making sense, Meath? It's doing the work for us by telling us the confidence interval for the estimate of the intercept. So it's using the uncertainty and saying, you want to be 68% confident that this is the true intercept. Well, the true intercept is probably somewhere between this and this. And it's just adding and subtracting close to, not exactly, close to 1 standard error. If you look at the numbers, they're almost exactly that. This is where the empirical rule comes into play with the 68, 95, 99.7. And it's going to do the exact mathematics for us, so we don't have to worry if we say, I want a... You going to do it for me? There we go. If I want a 99% confidence interval, it'll find them for me. So I'm 99% confident the true intercept is contained in the interval 54.82 to 57.87. So it's telling me the intervals itself to estimate what the true intercept and the true slope are, and it's using the uncertainty value right there to create it. We only have 2 more things in this output to talk about right here. We have the t-value, and the t-value is a really easy one to calculate. The t-value, let me go put summary again on the screen. The t-value, which is very easy to calculate, all the t-value is going to be your estimate divided by your standard error equals the t-statistic. If I blank that out in output, the t-value is a ratio of your estimate to your standard error. So what do you think you want the t-value to be? What do you think you want the t-value to be, Meath? Do you want the t-value to be large or small? Because it's a ratio. So the t-value is your estimate divided by the standard error, which is your uncertainty, equals to the t-value in this. So what do you want your t-value to be? What would you like your t-value to be? You'd want it to be very large, exactly. So what we could have is there's scenarios where the t-value is very small, and what would that lead to? We're going to look at we want to be close to we want it to be big. The bigger it is, the better. Great answers, Olivia, right there. Let's throw some more points in that. The bigger it is, the better. That is the answer for the t-value. Now, it doesn't matter if it's positive or negative because the next thing to look at is how the p-value is calculated. We will not calculate p-values by hand. It'll be done for us. If you were to get a t-statistic of 0, then we would ask, what is the probability of getting something as extreme or more extreme than 0? What percent of this curve is outside of 0? What percent of that curve is outside of 0? What percent of that curve is outside of 0? So if you go outside of 0, what percent of that curve is outside 0? Close, not 50%. Bigger the better. Not 50%. 50% is above 0. 50% is below 0. So not 50, but above 50, below 50. So total what? I see what you're saying right there at the 50, but above is 50, below is 50. So outside of 0 is what? Outside of 0 is what? And how would this occur? If we had a very small estimate of like 0.1, and then we had the uncertainty of this equals the estimate over the uncertainty. And this would be close to about 0. It'd be 100%. So think about this right here, this first scenario. All you basically have is what right now? If this is your ratio, all you'd have is what? If your t-statistic is equal to about 0, all you would basically have is what in your estimate? You estimate the slope or intercept to be 0.1, and then your uncertainty is 100. So all you basically have is what in your estimate? You're like, it's about 0.1, but I could be off by about 100. You're like, you basically only have what in your estimate? You have a ton of what? You have a ton of what right here? You're like, I think the intercept's 0.1, but I could be off by about 100. So all you basically have is what in your estimate? All you would basically have is uncertainty. You'd be like, I don't know what it is. Large uncertainty. All you have is uncertainty. So guess what? This has a p-value close to p-value close to 1, and that is not statistically significant. But let's change it up right here. Let's change the ratio of this. Your estimate and your uncertainty. So now your estimate is that the slope of your model is equal to, let's say, 6. And your uncertainty is 2. So what would your t-statistic be? You estimate the slope is 6, but you could be off by about 2. So what would your t-statistic be? Your t-statistic would be what? Your t-statistic is 3, which is the ratio of the two. So there's a ratio right there of 3. Now, the way this works when we do the p-value is you plot your results. That's where 3 is at. And then you plot a result just as extreme over here. Now we find the area outside the curve, which is the p-value, and the p-value looks a lot wider. The p-value here looks just visually a lot wider. And we could even estimate the p-value using the normal model and estimate it to be about this, which is the outside of a 99.7% confidence interval. It's a lot smaller, right? So using the normal model as an estimate, we know within plus or minus 3 standard deviations is 99.7, so the outside. So that's an estimate. Like if you ran a model and it came out to about this, you could use the normal model. It'll find the answers for you, but that's how the p-value is being calculated, is it's finding the outside if you go to your t-statistic and one just as extreme on the other side, because the slope, positive or negative, wouldn't really matter. We're talking about a slope just as extreme, so it could be positive, could be negative. So that is how the p-value is being calculated over there in the output right here. And these p-values, oh, go awesome. We'll do the GGplot here. Thank you so much, Olivia. We'll do that next. Thank you, 320, for being here. Hopefully this helps out a ton because we're doing this full output right here, mentioning every value in the order they appear. So are these p-values here statistically significant? Are these p-value here? Not, they're actually, William, good to see you here. These p-values are, let's think right here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. There it is. That's the p-value right there. The p-value on these, the last one, the p-value on the last one would be 0.003 about. It would be very model dependent on sample size because it does use t statistics, not z's. it's probably going to be a little bit bigger than 0.003 because the area outside on the t is always a little bit more than the z. So it's going to be 0.003 or greater, or technically 0.0027 because the exact on the normal curve is that. So it must be this or larger, theoretically speaking. So, but the good news is we don't have to find it like ourselves, because where is it? That value is right here, and we need to look at it to see if it is statistically significant. Does that make sense, Meath, right there? Like, we just need to look at that and say the intercept is statistically significant, and more importantly, the slope is statistically significant, because the slope is the XY relationship. So height has a significant relationship with weight. Does that make sense? What I garner from this is like height and weight have a significant relationship, where the way in which height explains weight is unlikely by random chance. So that's what I learned from that p-value, is like there is a significant relationship between height and weight. So now we're down to the last few things. Significant codes tell you by the stars. The star right here means it's basically, or it's between the bounds, excuse me, between the boundaries of 0 to 0.001. That means we have the 3 stars, so our p-value is contained in this region. Basically, if you see stars, it's what? If you see a star on your p-value, it's what? Because stars only start right here. If you see a star on your p-value, that's a quick way to know it's what. Like, you should just think any amount of stars, just that. Don't worry about the dot. Yeah, dot's not a big deal. If you see the stars, though, stars mean what? You see a star, boom, it's this. Because think stars start right here. You have 1 star between there, 2 stars, 3 stars. Statistically significant, exactly. It's the quickest way to tell on your p-value statistically significant. Statistically significant, you see it, you know it, boom. This right here is a dot, meaning kind of close. Don't worry about the dot. Then there's nothing if it's above here. If it's between 0.1 to 1, nothing. So important to know, it's just kind of letting you know a lot quicker statistical significance with stars. The next thing we have right here is the residual standard error, which we covered. If you're wondering what residual standard error is, that is literally what? What is the way we often talk about residual standard error? What is the 4-letter word? And check out this part of the video where we went in depth on what the concept is conceptually to explain it. Residual standard error is also known as the what. And then I'm going to interpret the value. Oh, William, that would have been awesome. Well, I'll be back. Are you going to be around for another few months? I'll be back, William. That'd be awesome. Thank you, William. That's really kind of you. Residual standard error. What is another name for residual standard error? What is another name for residual standard error? If you see residual standard error here, you should think what? Residual standard error is, it's just the RMSE, exactly. Residual standard error is the root mean squared error. And we could literally calculate this by going here to our survey 10, and these are the actual values of y minus the predicted. So this is going to get the predicted values from the model. There's all the residuals. So that's all the errors. So now we need to take the square of the errors. There's the square of the errors. There's all the squared errors. Now we go to the mean of the squared errors. This is the long way. So there's the root, or there's the mean squared error. There's the mean squared error. And now here's the root of it, SQRT. So there's the root mean squared error. Oh, it's SQR, right? SQR? Wait, what? Where'd I mess up? Warnings, NANs, square root. Root mean. Oh, wait. Did I square it? I squared the predicteds. I have the square on the wrong side of that. There we go. Something looks wrong, though. It's not squaring properly. 2 seconds. Got to go back. That's why I was going to write things out. So here is the error. There's the square of that. There's the mean of it. There we go. And there's the SQRT of it. There's the root mean squared error. But you know what? All that right there. All that for this. And it might have carried decimals a little bit differently, but all that for that work right there. All that work for 3.55. And it looks like it carried decimals a little bit differently, but so I did all this work right here for the root. That's the root mean squared error. And these inside of here could also be found a lot quicker. Instead of doing this work, we could have just gone here and said residuals of our model, which is also the errors, and those the same. The residuals are the actual minus predicteds. Rainbow get up top. But all that work right there is just to find the root mean squared error. And it might be not carrying all my decimals. Darn you are. Don't carry my decimals. Carry my decimals for me. So that's important right there. And what does that mean? Here's the interpretation. You ready? When I predict somebody's height, I'm usually off by about 3.5 inches. And you know what's really funny? Do you remember Brian's prediction earlier? When I predict someone's height, I'm usually off by about 3.5. I took this for you. Oh, that's awesome, Sam. That's Sam. Let's throw 1,000 points here. Sam, good to see you. I do remember your name in the chat, Sam. So good to see you. That's awesome in your recommended videos. 1,000 points right there. Thank you, Sam. That's a lot. That makes my day. I love when former students come by and then we throw some points. So think about this. We usually miss somebody's prediction. We usually miss somebody's height by about 3.5 inches. And then our model here missed me by 4 inches. So what would you say to Brian when Brian's like, you missed my height by 4 inches? What would you say? Like, our typical miss the model makes is 3.5, and then we missed me by 4 inches. So what would you say to Brian when I'm like, you were wrong by 4 inches. I'm 4 inches taller. You'd say, well, that's kind of close to what? Like, this value right here tells you what? How would you be like, well, yeah, I mean, we missed your prediction by 4 inches. That's your miss. Your residual is 4. We predicted you to be 71 inches. You're actually 75. We were wrong by 4 inches. You're 4 inches taller than the model predicted. So it is the typical miss the model makes. You'd say, well, your miss of 4 inches is about close to what our model usually misses people by. Does that make sense? Our model usually misses people by about 3.5. Now, it could be plus or minus. Does that make sense, Meath, on what it is? So, yes, Sam, nice. So, not really an outlier. It's close to it. Because when your friend says, I'll be there about 3.5, like about this time, I could be off by about this amount, that's saying we usually miss by about 3.5. It doesn't mean we will. It's like, we're usually off by about 3.5. So when Brian is missed by 4, we're like, that's about how much we're usually off by. We're usually off by 3.5-ish. So it's not perfect. We usually have a miss that's close to about 3.5. We won't miss by that for certain. I think a lot of times people say we will miss by 3.5. No, it's the typical miss. It's about how much we usually miss by. About when we do different predictions. So if you were to predict a bunch of people and then average together the square of the mean of all that good stuff, then you would see on average you miss by this, like typical miss. Does that make sense there, Meath? It's very important to make sure to say, when I predict people's heights, I'm typically off by about 3.5, so expect a kind of a window. We could be a little bit higher, we could be a little bit lower, but we're usually off by about 3.5. The degrees of freedom are used for calculation purposes for the T or the F statistic. That is going to be a T right there because it does not have numerator and denominator degrees of freedom. Not important right there. William right there, knocking it out of the park with some hours. Yeah, man, it's so good to see people back by 4 years ago. Like, oh no, William is just knocking it out of the park. Man, that's so awesome. William, got to get some more points here. We'll get some more points in the chat. Next, we have the R squared. R squared is what? How is R squared found and what is R squared? How is R squared found and what is R squared? How is R squared found and what is R squared? I don't think this format works for that. Oh, it does. It does. How is R squared found? Nice. How is R squared found and what is R squared? You might be up there at the top, William. William, you are, in terms of hours. Wait, why are you not showing up? There you are. You are in the top. You're very close to the top. You are 1, 2, wait, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. You're in the top 10. You're number 9. You're number 9. A few more. You probably know the people. You've probably seen the people who are there. Square the correlation. Boom. Take your correlation, square it, and you get R squared. R squared must be what? R squared must be a what number? R squared must be a what number? Think about this. R squared must be a what number? R squared has to be what? Yeah, nice job, William. You could probably name the people who are above you. Because if you think about the people you're in classes with who are, be like, oh, this person's here all the time. Like, positive in between 0 and 1. So it's a percent of variation in the y explained by the x. So when we talk about r squared right here, it's 36% of the variation in height is explained by the variation in weight. Yeah, 36. Have you graduated, William? If you want, and if you're on the Discord, we always want people to post about jobs and stuff in their companies. I'm trying to create where the Discord's more like you stay and you post about your jobs and your companies. So I'm hoping that Discord's a big help for people. Like, my dream is that the Discord is people are dropping by and being like, hey, my company's hiring, and like, hey, we want people here who are, because we got a lot of people on Discord really active and really great at helping people. So I know some people would be really great hires for companies. So my dream is we keep establishing. I graduate in May. I'm studying abroad. Nice, William. That's awesome. And so glad. Well, I'm just throwing you more points. I just love hearing that people are having these great things, graduating, doing study abroads. And if we want to have you get a great job too and all this awesome stuff. So thank you, William, for spreading the positivity and just swinging by to say, hey, that's what we love. So Meath, does it make sense how to interpret the r squared? Blank percent of the variation in y is explained by the variation in x. You want r squared to be higher. It has to be a number between 0 and 1. It's not correlation. It's correlation squared in this instance. So blank percent of the variation in y explained by the variation in x. So that's the r squared right there. We know what r squared is now. Now we go over here to the r squared adjusted. Now, we're not doing r squared adjusted for this assignment, but I'll interpret it. R squared adjusted is an r squared penalized, I can't even speak. So literally you take your r squared and you subtract off a penalty based on variables. So we're not interpreting it for today, but the r squared adjusted is a much more fairer way to look at your r squared. And here's the really crazy thing. If I make a really bad model right here, really quickly, random normal 100 numbers, tilde, random normal 100 numbers, it's mad at me, that's fine. Summary of M. Ooh, oh, what is it not like? Random norm. Is it not random norm numbers? Why tilde X? Oh, is it doing the same random normal numbers? Ooh. Let's store these outside the function then. Y, random norm, X, random norm. Might actually have a problem because of that. It might actually run the same if it's ran inside the function at the same time. Never tried that. Apparently don't do it. There we go. Okay. Now, what do you notice about r squared adjusted? What do you immediately see about r squared adjusted where you're like, what? What do you notice about r squared adjusted? We'll cover this a little bit later, multiple regression. What do you notice about r squared adjusted immediately with it in the output right here? Not, and so close to 0, yes. But remember what we said about r squared? R squared is between 0 and 1. How r squared is between 0 and 1. If the lowest value of r squared is 0, that's the lowest value of r squared is 0, and then r squared adjusted has a penalty term, that means r squared adjusted, so the formula is, like we'll look over it, is r squared minus a penalty for how many variables are in the model. R squared adjusted can be what? So very quick concept about r squared adjusted, because it's r squared minus a penalty term for how many variables are in the model. So it's a more fair way to look at our r squared because it'll penalize us for just throwing variables in the model. It's adjusted. Like, we're going to adjust it lower to be like, let's give a more fairer look at this. Like, let's not be too kind to ourselves on our r squared. R squared adjusted can be what? And it's not in this assignment, but I just wanted to do the full output right here. R squared adjusted can be what? Which r squared can't be. It can be negative. Because the lowest value of r squared is 0, and if r squared adjusted has a penalty on it, well, then r squared adjusted can be negative like that. There's no real interpretation of it, like mathematically speaking. Like, we can say it's r squared with a penalty on it, but there's no like exact comports to this. It's just a more fair way to compare models that have different amounts of variables, because models with more variables will have a larger penalty because the penalty is based on the amount of variables we have and also the unexplained variation. Like, I could look over the formula with you, but basically it's highly based on how many variables you have. Models with more variables and less or more variation unexplained will have higher penalties. So it kind of helps us not use junk models. It's a very good metric. Last but not least right here, we have the F statistic, which is going to be the ratio of the mean sums of squares that our model explains over the mean sums of squares for the residuals. So the F statistic right there comes from the output right here, which is the mean on average. Our model explains this for the variables in the model, compared to, on average, the remaining variation in the residuals is this. So the sums of squares, this is the good one right here, which is what our model explains. This is the reduction. We talked about that last class. And then this is what is left unexplained. Does that make sense to me? Like, we have explained about 5,000 of the variation. We have not explained about 9,000. Now, what you can do is you can take this and add them to find the total variation, and then look at what we've explained. And out of the total, we've explained about 5,000. And what did I just find right there? So this is a review also of last class, because now I'm looking at, there exists total variation, like the explained and the unexplained is the total. So we've explained this out of the total, and I've just found what right there by saying that's how much I've explained out of the total. That's how much I've explained out of the total. That's the R squared, the percent of variation explained. Like, this is what we explain, this is what we don't explain. So we explain this much out of the total, because you would add these to find out how much total there is to explain. The unexplained and the explained is how much variation there is. We've explained this amount, we haven't explained this amount. Total, there's this amount. So we've explained 5,000 units of the variation out of the 13,000 units. And you could also find this, last but not least, by making a the naive model. So the naive model could also be used to create this to find, there we go, that should be it. And if we look at the ANOVA of the naive model, I think, yeah, there it is right there. So that is the total variation that exists right there. And then we could look at our model and what our model explains. Now, that is the ANOVA right there, and good stuff. ANOVA output. So not too big, but the F statistic is going to be the ratio of what we explain. We don't interpret it that much, but the F statistic is the ratio of the, on average, our model explains this per how many variables are in our model. There's one variable, so the average amount of variation explained would be the same as the amount of variation per variable in the model. And then the average remaining variation in the residuals, this is how much total variation there is in the residuals. The sum of the squared error in the residuals is this. This is how many residuals there are, or estimates for the residual variation, and then on average. So that number right there, if you're wondering where that 12.6 comes from, it's going to be this divided by this, because it's a mean, it's on average. The F ratio right there, it's known as a ratio also, is the ratio of these numbers. And think about this. We like explaining things here, Meath. We like explaining things. So do you want your F ratio to be big or small? Do you want your F ratio to be big or small? You like explaining things. So the top variable is the explanatory variable. You want it to be large. You want a large F ratio. That leads to a larger F statistic. The F distribution looks a little bit different than the T. It's purely positive because you can't have negative variation explained. So the F distribution looks like this. A lot of times, really depends on the degrees of freedom, but oftentimes it's a right skew distribution. And the further over you are on the right, the larger the F and the whatter the what. The larger the F, the whatter the what here. What is this value over here shaded on the curve? The larger the F, the whatter the what. The larger the F, the whatter the what. The larger the F, the smaller the p-value exactly. And we see that in the output right here. Notice how it's statistically significant. You remember our random chance model we created previously? If we do the same ANOVA output, we can see right here, look, the F ratio is tiny. And the p-value, since the F is close to 0, the p-value is very close to what? Since the F is close to 0, oops, can't move that. Since the F is close to 0, the p-value will be close to what? With an F close to 0 over here, the p-value will be closer to 1. So does that make sense theoretically right there? Like, this model explains, this random chance model, which is a totally different model, does very little explaining, and there's lots of variation left in the residuals. So on average per residual, remember this is the average amount of variation per residual, mean error per residual, is very large, and thus we get a small ratio of what we explain to what is not explained, and this leads to a very insignificant test right here. And if you were to visualize this model, this is our M model, it looks like random chance. And notice how this is just horrible, horrible model. And I think we've almost explained all the output right here very much in detail. Last but not least, this p-value. Well, the degrees of freedom are the degrees of freedom to create the F distribution. We don't usually talk about those. Those are more statistical calculation ideas. Last but not least, the p-value of the overall model. So my overall model is statistically significant. which is actually the same as the significance of the slope and the random chance model. This is only in the univariate world with one x. Notice here that these two p-values are the same because your slope dictates the statistical significance. So the significance of the model, this is the significance of the model, is the significance of the one variable. Now this changes if you have two x's. If you have two x's right here, the significance of the model is just going to be that. So if you were to be in the multivariate world with two x's, that would no longer be, this is not the significance of the model. These are the significance of the x's, and this is the significance of the model right here. How are we doing right here, Meet? I know I went to the multivariate, but I just want to show that in the simple world, the slope is the significance of the model. Like these two will be the same in the simple world. In the multivariate world where you have multiple x's, this p-value is the significance of the whole model. Like what do the x's bring together? And are the x's explaining a significant amount of variation in the y variable of interest? And the answer is no right here. And this is, does this x bring with it new information? Does this x bring with it new information? In the simple world, it's what is the significance of this x? And this x is the only thing explaining, so it's the significance of the model. So that p-value down lower is the significance of the model. And up here, these are the significance of the x's, but this is also the significance of the model. How are we doing on this? That's the full output right here. We should have every little bit of this explained right here. Every little bit of this. And then I think we're going to do some ggplots here. Everything should be explained right there. Is there any question on any of the output right there? Awesome. So make sure we did this in order. If you're watching this, check this out. We did every bit of that in order. Took a good 40 minutes to do, explained fully. So let's do the ggplot here now. Let's say awesome ggplot for regression. I love some ggplots. This is my fun right here. We're focusing a lot on 320 today. I want to make sure people have, I know a lot of people have been asking for help in 320. Want to make sure you have a video right here. That's the full output right there. The confident, we talked about a little bit through this, and it's confidence intervals to estimate. So I think this is all the code you need. Confidence intervals to estimate those values. No, ggplot is awesome. I'm a huge fan of ggplot. Let's go. We'll put a break in the video. And you know what we're going to do? We're going to Google. Okay. So the number one thing to do if you're ever trying to make ggplots is to Google how to do them. Because the code is constantly updating. ggplot to regression line. People are constantly making better and better ggplots. No joke, I've already even went to this page. So someone's got Stack Overflow 2016. We probably want to do better than that. GGpubr might have really good stuff for that. Let's take a look at our GGpubr. So first thing you want to do is load library GGpubr. It's probably going to load ggplot if you want to make sure ggplot2. And I like to use library ggeasy also for things like centering titles. It's got other stuff too, and I really should learn more about the library ggeasy because it's meant to make ggplots easier. So now, let me go and look inside of the package GGpubr. There's GGpubr. So you can actually look inside and look at the functions. GGscatter hist, that's going to do border histograms. We could probably use GGscatter right here. So because we're going to make scatterplot. That's what a linear model is created around. So let's go here and look at the GGscatter and look at how to use it. Okay. So here's the GGscatter. It's got tons of things. Facet, I've been using some facet grids lately. Facet grids makes multiple plots for you. Woo, look at this. This looks cool right here. Oh, this looks so cool. We got our X, we got our Y. Something tells me all we're going to need to make. And it's got the correlation. Oh my gosh, look at this. A basic plot. We don't want to use the LOS method. That's going to do local regression. I always hate what's called LOS. Local regression. I always forget. It's finding a regression line or a kind of a smooth line around a local area. I always hate that's called LOS regression. It should be called loc regression. Loc-reg. That's what we came up with in the class. I'll probably forget a week or two from now. LOS regression, what is that again? Local regression. Just call it local regression then. They try to make abbreviations. Called loc-reg. Okay. So we are using our same data right here. And we're going to change the data frame. This has to be in quotes now. It's just the way it takes the arguments. And we might get it right here. This might do everything. Don't like the way that... Looking pretty good. It's... The limits right here are pretty bad. But there's your... We've got the value of R. I don't like the way that R is rounded. That's showing the R squared, I believe. How are they... Who wrote this? Because I don't like the way that's... Method Pearson. Oh, that's the Pearson. Okay. Label coefficient arguments, coefficient, correlation coefficient, add correlation coefficient, true. And then list method my Pearson's label X. Oh, so it's putting it, this is part of the issue. It's putting it over there on this side of it. So we need to move the X part of this to like 60. There it is. That's it's pretty good right there, right? I mean, overall, and this is a confidence interval for the true mean of the model. Add reg line, add parameters, color blue, fill light gray. So that right there, let's go to fill equals hashtag FF8200. Hey, I like that right there. There we go, a little bit better. So many things you can do. Yeah. How's that look right there, Meath? And I want people to think about how long this took us to do. How long did it take us to make this? I just took everything they had. I went to the help, and you can copy these. You just got to change your X, you got to change your Y, and then with that, you can go over here and you can make your graphic. Even better, you can export them as files right there. So you could import, you could take them. Looks pretty good, right? You've got your R. Not long, copy and paste is great, exactly. And then you kind of you can look through here and be like, okay, if you want it to be just orange, that's the hexadecimal color code for orange. You can see a small change between the orange. I'm using the hexadecimal color code for UT orange right there if you want. I love that they added custom regression line right there. Add reg dot line, so they're in the regression line there. Color black, so you can make your points different colors if you want. You go purple right there, you get some purple points. Just all depends. Is it hashtag 000000? That's black right there. So let's go CC. No, I want to go. Let's go 3-3. No, little red in there. Little red. I don't know. You can look up hexadecimal codes. You can make any color you want. No, just messing around with the color code. The shade. The shape is going to be. There's a GGplot. I'll show you. There's a list of GGplot shapes. I've looked it up all the time right here. So GGplot to shapes. And here's the list of the shapes right here. That's a horrible view of them. Really, there we go. So we're on shape 21, which actually has a fill. Shape 21 through 25 has fills that you can use. So if we were to add a fill right here, the shape should have a fill now. We're going to add another argument. We're going to say fill equals blue. And we should get it. There we go. Oof, we don't want that. So we want to go something like very light color. So FF88FF. It all depends. Go even lighter. CC. All depends on what you want. All depends on what you want. This is purely customizable right here. I'm going to remove that comment right here. But I just have fun using this. Now, if you change this to another value, you won't get the fill. Those don't have fills. Oh, it's doing the fill right there? Oh. No, it's not. It's just that this is purple. There we go. Now it's black. So if you say something like pink right there, black, pink, you have to do that. Oh, 21. I thought 21 was the inner circle that has the fill. Oh, size. Look at that. I went to the size metric. There we go. Now we should have it. There we go. Wait a minute. What are you wondering about, Meath? What are you wondering about? Let's look a tiny bit more because it's got correlation coefficient. Nothing. Awesome. It's just there's so much fun you can do with these. Like so many things you can do. Core method, core this, core that. I don't really care about correlation. I want to show GG theme. We'll do a GG theme here in a second. Label, family font, mean point size, ellipse. you can do ellipses, ellipse. Yeah. So you can look at the things they add. A rug of the points. I don't really care for that. Palette, the palette that's using, the colors, and a lot of good things right here. If you just use their templates, you can usually find something decent and kind of see how things work. Like to completely do it differently, you could take this GG scatter right here. Probably be a bit less complex. Once again, we're just going to take our arguments we already have, drop them in right here. Now this one is using a color, so we want to remove the color because that's a categorical variable. You could technically do something like this. This should run. It did it. The name thing. Ooh. So label name, we don't want that, and we don't want the repel. So that's not going to work for ours. And then we have too many colors in the palette. And here we are right here. And I wonder if we could fit the lines to this. If this fits 2 models, that'd be insane. So if you look at the minimum, this is not what we're doing right now. We're not doing indicator regression. But I am interested to see if we just add regression line to this, if it would actually do it and make the formula it is doing it. A little hard to see right there. So you might try to do something like FF8200. There's your orange. That's even worse. And then we could go right here and say blue. And then we probably need to make the color of the regression line different. Add parameters. There we go right there. It's not too horrible. But I just always find it really amazing what you can do. Ooh, color equals blue. So now we want to probably do a list. Ooh. Or can we do color equals blue, comma, red? It doesn't like it. Probably wants list. I've never done 2 regression lines with this. Color equals list, concatenate vector. Unknown color, blue, comma, red. Other known color name, blue, red. Yeah, it's mad about that. Well, I've never done the 2 regression lines. We are kind of getting there. Don't worry. This was just kind of a idea of what we could have, and we'd want to make this look better because it might be a little, I don't know. That's not too bad right there. Does that make sense there, Meath? Like, this is not that bad of a graphic if you ask me. It's showing 2 separate regression models. It's not actually doing indicator regression. It is, I believe, 2 separate regression models right there. Yeah, so not too bad creating 2 different regression models, and we're not doing that right now, but that would be 2 separate regression models, one for males, one for females, predicting people's heights from their weights, and you can see the stronger slope for the one line. But pretty quick models, and I would use something more like this. So if you remove out gender right here, you will get something more similar to what we're doing. And now we have this, and you could go through here and change the color of the line, add params for the line. So you go back into here, add the parameters for the line, and now the line is blue, and the fill didn't come into play. Confint, we need confint for the line. And there we go. Is there a prediction int? No, it doesn't have predictant. That's interesting. Let me look at one last thing, because I wish it had prediction intervals, because I'm going to be using this. Confint, there's confint. Prediction int. No, individuals? No. Doesn't have a prediction interval, which is a bummer. I made GGplot with 2 lines before, and different axes is possible. I'd imagine making one GGplot with 2 models would be very similar. You can actually do the 2 axes pretty quickly. It's sec axis. I did it last night, actually. It's so funny you mentioned that. You can throw 2 axes on a plot. The argument is, I've got it over in like another screen for some work I'm doing. The argument is, I've got it all right here. Oh my gosh. I'll show you some of the code I've been writing right here. I'll grab some of it. Here is part of the code I've been writing. This is just part of it. This is part of the code. Part of the code I've been writing right here. And so the sec access right here, all that right there, there's part of the code I've been writing. Like that is about 25% of the code for the graphic. I'm eliminating certain things in the theme. I'm changing the fills. I'm changing everything. But I think I have like 100 lines for one graphic. And the graphic looks awesome. So you change everything. So the options of what you can do, I use Victorian Electric data and graph temperature and demand. Yeah. So we use GGplots because it's called the grammar of graphics for a reason. Like, you could make some really amazing plots with GGplot. That's the point of it, is like to make really awesome graphics. Because, William, how hard is it to add a title to my plot right here? We haven't even added a title to this. And we'll look at the last few things. It was like 10 because I'm a person. How easy is it? Well, adding a title. How would we add a title to this? How would we add a title to this plot? How hard is it to add a title? Stupidly, I like that. Just so easy. GG title. My title right there. Boom. How easy is it to center that title? Easy center title. This comes from GG Easy. There we go. Easy center title right there. Plus GG title right there. And then what you could do is you could go right here and go to GG theme. So GG themes, it's theme. Theme is the name of it. Theme calc. And there's a different theme. Theme Excel. You can change the theme just instantaneously by going to all these different themes right here. Theme update. There you go. There's that theme. Theme this. Maybe you'll settle on probably a favorite theme, but you can change it just instantaneously by changing. I wish you could like. There should be a thing called like theme browser. Oh, I should write that code. I should write a code that's called 538 is fresh. Boom. Theme 538. There you go. 538 right there. Just change the theme of it just like this. So once you learn how to do this, you can just change between. Ooh, we don't like that. We don't like that. That removed out a bunch of our stuff. Solarized. You can just change your theme instantaneously to different ways you want your graphics to look. Theme gray right there. Not the bad. Whatever you like. Change your theme. Change everything. It's pretty easy to do. Just add on the theme change. So that is an argument, or that's a function rather, that just changes the theme. It sets different things. And then I put my title afterwards and my center of the title after that. So that way it changed the theme, then it threw on the title, and then it added it. You have to think about the order of which things occur, because you have to be careful, because I've done this before. Some themes will reorder your title. So if you go to theme of base or something, it might put your title back over there. But if you put the theme back over here, then when you run it and you will change it. Oh, we got a plus. Look at that. So we got this down here. Now when you run it, it'll center the title, because the centering the title happens afterwards. How's this looking, Meath? We got class here, I think, in 13 minutes. Ah! Does that make sense? And I really love making graphics. I think making graphics is one of the funnest things to do. Like telling stories with data. This is really where you can excel and show people your skills. So class in 12 minutes. See you soon. Click here. But we did the full output, which I think explains about everything. I'm trying to think of anything we would have missed. Sending the announcement to the class. Which class? 474. 474. And what's even cooler about this, watch this. You take your graphic. Now you can't put this in your Word. Can't knit this. Library Plotly. And now you have an interactive graphic. Now you literally have an interactive graphic right here. You have I might even take a picture of that. Thank you, Amanda, right there. Liked 474 a lot. Nice. You can zoom in on this. You can zoom into regions. You could hover over the line, see the predictions. So you can get the at a weight of 90, we predict a height of 54. You can literally just use this to make predictions too. You might need to like zoom in and be like, okay, at a weight of 163, we predict 70 inches. And you can see over here, or no, at a height of about 70 inches, we predict 167. So that would be over here on the line. So you can move the axes. You can just do anything you want. I wish it showed the lower numbers. I think because we didn't put those in. I could, I guess, write those in. But yeah, you'd have to, I guess, add the scale. Okay, let's see if Brian knows how to do this, because I've been working a lot. Scale, Y continuous. So now we want to do breaks equals sequence going from -50 to 400 by 50. Oh, no. Come on. I thought it should show it. Y-lim. It is doing it now. What? Why did it change it back? Oh, because I don't have this. Show me the number. Show me that number. Ooh. Oh, whoops. Oh, let's go Y-lim here. It's my last thing. I want this to work. I've been practicing my GGplots a lot. Okay, so the scale continuous breaks. Should be what scale Y continuous. That should be it. Names, breaks, minor breaks, end breaks, labels. Breaks equals that, label. Let's put labels here too. I've done this so much lately. Awesome idea. Let me run the graphic here on this and see what it makes. Equals equals. Ooh, it doesn't like it. Well, I need to practice more on my GGplots. Need to practice more. I've been doing it so much. Look at my other graphics I've been making. Snaid here, nice job. With that, I got 8 minutes. I'm going to go grab some more food. See you soon in class, everyone. Bye for now.